Ever wondered how systems detect weird patterns in data that changes over time? Like how a factory monitors machines to catch problems before they fail, or how your phone spots unusual activity that might mean a security threat. Today, we're diving into a cutting-edge approach to anomaly detection, spotting the weird stuff in time series data. And it's all about adapting to change. Let's start with the basics. Time series data. Think of it as a stream of numbers over time, like stock prices, sensor readings, or even your heart rate. The challenge: these datasets aren't static. They shift trend and sometimes flip completely. Traditional methods like setting fixed thresholds, e.g., if it's more than 3 standard deviations from the mean, it's an anomaly, struggle here. Why? Because if the data's behavior changes, say a machine starts running hotter due to wear, those old thresholds go out the window. Enter segmented confidence sequences, SCS, and multi-scale adaptive confidence segments, MACS. These are 2 new frameworks from researchers at NVIDIA that tackle this problem head-on. Let's break them down. First, SCS. Imagine you're listening to a song. The melody might change between verses, choruses, and bridges. SCS does something similar with data. It segments the time series into parts where the data behaves similarly. For example, if a machine's temperature rises gradually over days, then spikes suddenly, SCS splits the data into distinct regimes. Within each segment, it calculates local confidence bounds, statistical ranges that adapt to the specific patterns in that chunk of data. This means it's not stuck with one-size-fits-all thresholds. If a new data point falls outside the local bounds, it's flagged as an anomaly. Cool, right? And because it uses something called Hoeffding's inequality, it even guarantees a controlled false alarm rate, so you don't get overwhelmed by false positives. Now MACS takes it a step further. Think of it as a multi-tool for detecting anomalies at different speeds. While SCS focuses on local segments, MACS looks at the same data through multiple lenses, short-term, medium-term, and long-term windows. For instance, it might track a 50-step window for quick spikes, a 100-step window for moderate changes, and a 500-step window for slow trends. Each window has its own confidence bounds, and MACS uses an attention mechanism to weigh which scale matters most based on the data's current behavior. If the data is volatile, it pays more attention to short-term changes. If it's stable, it focuses on the bigger picture. This dual approach catches both sudden glitches and gradual shifts, like a machine slowly degrading over months. The results? The researchers tested these methods on real-world manufacturing data and saw big improvements in accuracy compared to older techniques. Traditional methods like rolling quantiles often miss anomalies or sound the alarm too often. But SCS and MACS adapt in real time, making them more reliable and interpretable. So why does this matter? In industries where downtime is costly or safety is critical, like energy grids, healthcare, or autonomous vehicles, being able to spot anomalies early can save lives, money, and resources. Let's dig deeper into how MACS works. Unlike traditional methods that rely on fixed thresholds, MACS dynamically adjusts to regime changes, sudden shifts in data behavior. How does it know when a regime has changed? It tracks 2 key metrics: the normalized change in mean and the standard deviation. If the average value of a dataset swings too much or the spread of values becomes too erratic, MACS flags it as a potential shift. For example, if a server's CPU usage suddenly spikes from a steady 20% to 80%, that's a red flag. But here's the clever part: MACS doesn't rely on a single check. It uses a dual detection system. First, it looks for points that violate thresholds in multiple scales, like checking if a value is odd in both short-term and long-term trends. Second, it uses an attention mechanism to weigh the most relevant patterns, much like how your brain focuses on the most important details in a chaotic scene. If both systems agree, it sounds the alarm. Let's walk through the process. MACS starts by analyzing data at multiple time scales, like zooming in and out on a map. It calculates confidence bounds for each scale, then combines them using adaptive weights. This helps it catch both sudden spikes and slow, creeping changes. When a regime shift is detected, the system switches to a regime-aware mode, requiring both detection methods to align before flagging an anomaly. This prevents false alarms while keeping sensitivity high. Finally, a percentile-based filter weeds out minor fluctuations, ensuring only significant outliers are flagged. It's like having a filter that separates real threats from background noise. In tests on datasets like semiconductor manufacturing data and server logs, MACS outperformed traditional approaches. For example, in a wafer manufacturing dataset, it caught twice as many true anomalies as the old 99th percentile method, without drowning in false positives. The key: balancing recall, catching real issues and precision, avoiding false alarms through its adaptive, multi-layered design. But the real magic is their flexibility. By tweaking confidence levels, you can control how sensitive the system is, whether you want to catch every possible issue or avoid too many false alarms. And unlike some methods, they work without needing labeled examples, making them perfect for real-world scenarios where data is messy and unpredictable. Looking ahead, researchers are exploring ways to apply these ideas to more complex data, like multi-dimensional streams or systems with hidden connections. The goal? To make anomaly detection not just smarter, but more intuitive, like a seasoned expert who learns as they go. So next time you hear about AI spotting a problem in a factory or a network, remember, it's not just about rules. It's about systems that evolve, adapt, and stay one step ahead of the unexpected.